Okay, good morning. Welcome. Welcome to this last lecture. It's already the last one. So I will first start with a quick summary of where we are. And so today we are here. So basically you had the lab on feature extraction, object description last week. And as you have seen in the news, there will be open hours, office hours again this week, so that you can come and ask questions to complete this lab and give your report by the next lab, which is by next Friday, right? When you upload your report on Moodle, please do not forget to submit it, because you can upload it in draft mode, and 10 of you forgot to submit it. It's not a problem. We understand it's every year since 20 years that is the same, but please do submit. A few of you did not submit the first lab. I think 5 or 6 of you did not. So I just would like to know whether you decided just not to submit, that's live, because you're too busy, or whether they withdrew from the course. So I send them an email, but if some of you are here and you decided not to submit your first lab, just let me know, because it's important for me for scheduling the exam, the interviews, okay? So just let me know, and I also say that for those who will listen and watch the video. Yes, please.
It's actually, I never had the submitting thing before, in 4 years EPFL.
Really?
So I wondered if you knew that.
We always had that.
If you there is another method to
There might be a setting that I don't use or that I use, which allows you to submit in draft mode.
Yeah, you can just always change your things, but as soon as the delay is over, you can't change anything anymore. So the last thing that is online is submitted automatically.
Okay. Well, to tell you the truth, I don't enforce the deadline, so which allows you a little bit of flexibility. So as far as I can see, let's continue with this system, which allows you a little bit of flexibility. If you don't want this flexibility, I'm happy to enforce the deadline. But let's say it's okay, okay? No, but so don't forget to submit. Okay, so office hours next week, lab on classification on Friday next week on the topic that we will see today. I think you will have fun again. You will design a multi-layer perceptron and do classification. So, you know, a little bit of introduction to machine learning. As usual, well, according to your request, you will already have the data and the description of the lab early next week, hopefully on Monday. So you can start already. And we will again have office hours the week after for you to complete that. Okay? That's okay? So, and after that, we will start the special project, the robot. And again, I think this year, I think you will have fun. It's something that we designed such that you will basically reuse the routines that you have already done for the labs 1, 2, and 3. So it will be basically assembling everything in a real live and real time implementation. You are many this year, 46, something like that. We will have the final presentations on that day, 1st of June. It will be tough and tight. So, you know, it will be like a challenge in organization to have all of you presenting there. We will ask you to do that by groups of 3. You can think already, because it's already quite a lot for a single session. And before that, we'll have the interviews. And I know many of you are waiting to know what it will actually be. So it will be very, very simple. I mean, it's a 10 to 15 minutes interview, depending on the schedule that I will finalize today, where we will basically review. We will pick questions, 2 questions, randomly, and you will have to talk about what we have seen on those topics. That will be on 18 and 25. And for your convenience, and mostly for the convenience of those of you who are not here today, I will also extend that to either the afternoon of those days or the day before, the Thursday before. So I will today, hopefully, by Monday, let's say, have a doodle with slots, not 15-minute slots, but 2 or 3 hour slots, allowing you to give your preference. I really ask you to be fair. Put your availability as much as you can. If you only put 1, and if everybody chooses the same, I will be in trouble. So if you really can make yourself available at different slots, please indicate it. It gives me more flexibility. And if it really doesn't work, I will impose the schedule assuming that if you register to this course, you can make yourself available for this slot here. A slide. And again, it doesn't apply to you guys. It doesn't apply to those who are watching the video. Okay? Hopefully they are doing, at least. Okay? Clear? So now let's move to the course. And I hope you will enjoy the course. This is by far my favorite course, my favorite lecture. And you will see why. And actually, I lost my mouse, so I will use this as a pointer. So what we will do today, oops, already wrong, is in my famous, where is it? Yes, it's coming. I have really to try to learn this stuff. Normally, if I click, it should work. Doesn't. Oh, come on. It's supposed to be connected. It doesn't work. Okay, I think I will do that. We are here. We are here. So basically, you know everything about segmentation. You know everything about object description, right? And so you will know everything about classification today. Hopefully. So basically now we are dealing with the output of a descriptor, which is a series of features. It's a feature vector. So we are not dealing with images anymore. We are not dealing with any images anymore. We are not dealing with objects anymore. We are dealing with features, just vectors. And we will try to come up with a decision, whether this vector belongs to class 1 or class 2 or class n. Okay, that's really what we are going to do today. So we are going to talk about the basics of machine learning. Let's say the basics of artificial intelligence. And the basics of artificial intelligence is basically statistics. And you will see that's really the foundations of artificial intelligence and machine learning as it is seen today. And I will definitely not go into the details of the most advanced machine learning techniques. I will even not probably, well, I will mention, but not detail anything about deep learning and so on. You have specific courses on that. But I want you really to understand the foundations. And this allows you, again, to really approach this very fascinating world of machine learning with a mathematical context. This is important. This is not just a black box. There is math behind it. And when you have done that, you can act in the real world. So what are we going to see? You are now the most renowned experts in object description, right? You're able to extract fantastic descriptors which have a very small intra-class variance and a very large inter-class variance because you are the experts. So you managed to do that. That's fantastic. So now we live in a feature space. Each image, each object that we want to recognize is actually just described by a point in the feature space. This is a 2D feature space in my example, but it can be any dimensional feature space. It can be n dimensions. And remember the curse of dimensionality. You should take many features to describe correctly your objects, but not too many. For my examples that I will use here, of course, I will be in a 2D feature space. This is just for the sake of representation. You really have to imagine that this feature space can be any dimension, but still you have, in that feature space, each object represented by a point. Clear? So this is the example of where I have the amplitude of the first and the second Fourier descriptor for recognizing digits, 1, 2, and 3, very close to what you have done in the lab. And it appears that with those features, they are not that bad because they cluster nicely for all the ones in one corner, for the twos kind of in one corner, and for the 3 here, although you might recognize or not that there are some crosses there that are leaking towards the other class. But roughly, it's not that bad. Our job today will be to see how we can build a system that will recognize a new object. You give a new point, that one, right on the line, and the system will tell you, oh, from what I learned, this is a 3. So you give the features, it will give you the class. And that's what we will see today. Use the classification rule to classify a feature vector. And I would like to start with some intuition, because it's always good to build the intuition before seeing the math. And so let's take an example of objects. And those objects are biological cells. The application itself doesn't matter. And as you can see, they are cells with a mean gray level which is quite bright, and there are cells with a mean gray level which is quite dark. And there are cells with a variance of the appearance of the gray levels, which is quite low, and there are cells with a variance of the appearance, the value of the pixels inside the cell, which is quite large. And so for this application, as I'm also a specialist in feature description, I decided to use the mean and the standard deviation as two features to allow me to classify those cells. That's my decision. Okay? So I live in a two-dimensional feature space with the mean and the standard deviation of the object that I managed to segment because I'm also a specialist in segmentation. Okay? And so what we will do is basically ask a biologist to give me a series of images of class 1 and a series of images of class 2 just for me to train myself and to train a system. So I will use that to learn what are the characteristics of the cloud of points in my feature space corresponding to class 1 and to class 2. And I will learn that. And then when I receive a new one, I will be easily able to say whether it is in class 1 or in class 2. All right? Okay, right? So basically, that's what you have here. The new point has to be classified. We work in the feature space, and our role is to build a classifier that will learn. And in my example, the classifier is very simple. It's a line. This is called a linear classifier. And the rule is simple. If my new point is on that part of the line, it's class 1. If it's on that part, it's class 2. And that's the basics and the main description of what a classification is. When you build a classifier, when you train a classifier, what you actually build, what you actually train, is a partition of the feature space in different regions separated by a decision line. It can be a straight line, it can be a complicated line in 2D. In 3D, it can be a plane or a hyperplane. And in ND, it's a surface or a hypersurface. But still, in the case of two classes, you want to partition the feature space in regions separated by a decision line. Being on one side of the decision line, you are in class 1, in class 2 in the other. If you have more classes, you have different decision lines, and you have to be on the right of decision 1 and on the left of decision 2 to be in class 1, 2, 3, or 4, for instance. So you combine the classifications. So that's basically what we will try to see. So I would like to start with intuition. Can you please give me ideas on how to build this line? Why did I put this line here? And I want you to really come with crazy ideas or intuitive ideas. Don't worry if it's true or wrong because you already had machine learning courses and you know the true answer, maybe. Give me ideas how to build this. And what I will show you is that your ideas are not that crazy. So please, come with ideas. I would like to have 2 or 3 different ideas how to position this line exactly there. So please, yes?
You know that there is a round and cross, you know the classes?
1 and 2, yes. I have this training set. This is called the training set, obviously.
You can take the central point of each class?
Yes, I take the mean, because it's a vector space. I take the mean vector here and the mean vector here, okay, and then?
And then you take the middle of the distance.
So I draw a line between the two, and I take the middle, and then?
Then you have a point where you know you
Sure.
really,
correct. And then you still have to choose that. Let's make it perpendicular.
Yeah.
You agree? So this is your proposal. The line is the line that crosses the line of the centers in the middle and perpendicular to it. And what you will see is that it's a very good idea in some cases. Please, give me other ideas. A log regressor. So on what? Well, but if you do a log regression on data points, you will basically have that line, the best fitting in the space. Here we have 2 clouds. So how do you do a log regression on 2 clouds?
Not a linear regression, logistic regression.
Logistic regressor. Okay, that is a bit more advanced. Okay, I'm not sure I want to enter in this idea, but I take it. Okay, more.
You could start with just a lot of random lines.
Yes, and
see which ones fit best, and then maybe more.
What do you mean by fit best?
Or which ones best separate the two classes.
What criterion do you use?
Not fully sure.
Hmm?
Maybe.
You have the points with their correct labels. So how do you decide that this line is bad?
That it misclassifies.
Correct. So you will basically try to learn the line that makes the smallest number of errors. Very good. This is a linear perceptron. Or it's already a neural network that you have describing there. We'll see that at the end. Anyway, last one.
I don't know if it's the same idea, but I think you should maximize the margin.
Aha, fantastic. This is a support vector machine. Very good, thank you. Oh, fantastic. Okay, I think I have what I want. So now we'll describe, we will go through maybe your ideas or put a little bit of theory behind that and see that indeed some of your ideas correspond to some of the variations of what I will see. So keep in mind what you said, and I will try to also keep in mind. And we'll now describe in which case all your ideas would fit. Okay? Correct? We do that? Okay. So your idea was to say, I take the center, I put the line. Very good. Now I take exactly the same, another data set. So in that case, the line is here, right? And this point is classified there. Now I take another data set with the same mean, but something else. Same mean. Now, intuitively, this part being a little bit more compact, intuitively, the line has to move downwards because this one being more compact kind of tells me that the class there is more compact. And so the points here would already not belong to that class. It's already too far away as compared to what? These points now, because it becomes already a little bit too far of that, using what as a measure? The variance. So somehow, your idea is okay, but somehow we should also consider the distribution of the points to say whether the line is here or here. Imagine now that this class is much more probable. If this line is much more probable than this one, then we will kind of push that line away to have more prior on that class. So we have to play with those quantities. In some case, we will use the mean, but a little bit more generally, we'll use the mean and the shape of the distribution. And also, we should use the prior probability. And you see that we immediately come into the question of doing probabilistic classification. And the machine learning is a derivation of that. But I want to start with really the idea of probabilistic classification. The term is Bayesian classification. So this is what we will use today. Keep in mind your propositions and we will discuss them. What is true, what is sure, is that we have a training set. So we are in a domain that is called supervised classification. We ask the biologist what happens. Sorry for interruption. So let's continue. So, where am I? Yes. So we have a training set. We are in a case which is called supervised classification. So basically, we have a training set, and this training set is labeled. That's the definition of a supervised classification. We have a training set to train the classifier, and in this training set, we have the correct labels of each individual in the training set. We know which one belongs to which class. So from that, we can build a classifier. And we will see what is a Bayesian classifier. Then we will see linear classifier. That was your idea, I think. No, I don't know. It was your idea. And we will see nonlinear classification in neural networks, and we'll see a little bit also about more advanced stuff. There is another series of classification that we will see at the very end, which is the case where you receive a training set, you receive data, but they are not labeled. They just represent the reality, but you don't know which sample belongs to which class. And we'll see how we can still deal with that to build a classifier. This is called clustering. But first, the most of the course will be dedicated to supervised classification. So what are we going to do? First, Bayesian classification. Because when we are talking about probability of belonging to class 1 or class 2, we will quickly see that this is framed as a Bayesian problem using the Bayes rule. And so the goal will be to build a classifier here which will classify a new object that you will show in the most probable class. We will estimate for this individual that I receive, based on what I have learned, what is the probability that this individual belongs to class 1 or class 2? And we will obviously assign it to the class that is the most probable. So we will have n classes, we will have a new feature vector, and we will define that this new object belongs to class I if the probability of the class knowing the individual is bigger than all the others. So this is the Bayesian formulation. I want to estimate what is the probability of being in class I when I see that object, that feature vector. So this is the quantity that we need to evaluate for each of the possible classes, and then the classification rule is simple, the highest probability. That's exactly what we will do. So now, let's go. We will consider a two-class problem. That's much more simple to express, but this generalizes very easily. And so what we want to estimate is this probability for class I when I observe object X. And by using the Bayes rule, I can write that like this. And you remember what we have seen for the threshold, the statistical threshold, the optimal threshold, when we wanted to threshold images. Here we are working just in an n-dimensional space, but the rest is the same. This Bayes rules tells me that to estimate this probability, I need to estimate what is this, and this is the distribution of probabilities of the possible features when they belong to class I. So this is the PDF of class I. This is the prior probability of class I. What is the prior probability of an object being in class I independently of its features? There are more, I don't know what, cells of type 1 than cells of type 2 in the world. That's life. And this is the joint distribution. This will be the same for all the classes, so I can ignore it, and it's a probability density function, so it's positive. So now my question for the two-class problem is simple. Is this bigger than that, or that bigger than that? And this rewrites like this. Now, what is, in my feature space X, what is the equation of the line separating the two classes? What is the equation of that line? Because this creates a partition of the space. There is a part of the feature space where this probability is bigger than this one, and there is a part of the feature space where this one is bigger than this one. And there is a part of the feature space where those two are equal, right? What is the equation of that surface or that line in the feature space?
The set of points that put that equation equal.
Exact. So it's basically the set of points where this equals this, or where this minus this equals 0. Right? So let's keep that in mind. So in my typical one-dimensional example, you remember, we will have a way to estimate those two prior probabilities, those two distributions, sorry. We multiply them by the prior, and the separation line in 1D, it's a point, is the point where this meets. And this is the classifier that will minimize the probability of error. The probability of error, remember, for class 1 is this one, this surface, because this is all the points that will be classified, for class 2, sorry. This is all the points that will be classified in class 1, while they should be classified in class 2. Okay, so far so good. Generalizing to n classes is simple, and as we said, the decision surface in ND, not a line, it's a surface on a hypersurface, is the set of points that verify this equality. So now when I received a new point, I will evaluate that. If that is equal to 0, bad luck, I'm on the surface. But if this evaluation is positive, what does it tell me? So I classify in class I. If it's negative, I classify in class J. So basically, my goal now from the training set is to give an equation for that expression. And then when I receive a new point, the classification is very simple. I evaluate this expression for my new x. If the result is positive, it's class I. If the result is negative, it's class J. That's it. Just evaluate the sign of the evaluation of my equation of the decision function at point that I want to classify. Right? And in some cases, this surface will have a very simple expression. In others, it might be complicated, but that's okay. Okay? So that's the basic idea of the Bayesian classification. You express the equation of the decision line, and then you evaluate its value at the point you want to classify. If you are not lucky, it will give you 0 and you cannot decide, but it's very unlikely. But if it's positive, you are in the first part of the class, the space, class I. If it's negative, you're in class J. You can say in class 1 and class 2 if you are in just a two-class problem. Huh? Okay? And now depending, of course, on the PDF of your class, this expression might be more or less complicated. But obviously, we'll use the Bayes rule to express that. And learn the equation of that surface from the training data. Learn the equation of that from the training data. Now, let me open a parenthesis. You agree that this bigger than that, or this minus that equals 0? No. You agree that the equation of the surface is that one, but it can also be, where is it? That one. What is that? If I take P, and I calculate actually a function of P, where F is a monotonally increasing function, then you agree that I can replace P minus P, Pi minus Pj, by Gi minus Gj, because it doesn't change the relationship. If G here is monotonally increasing, that being that one bigger than that one, or that being smaller than that one, remains valid by calculating Gi being bigger than Gj, or the opposite. Huh? Agree with that? Yes? Sure? Yes? Okay. So, why do I do that? I close the parenthesis. This is just a trick that I will use. But you have to agree with me that the equation of the decision line, of the decision function, which is called discriminant function, by the way, is Pi minus Pj equals 0, or equivalently, Gi minus Gj equals 0. If I choose F as a monotonally increasing function. Why I said it this time. Yes? So now, what are we going to say? We are going to say, to try to learn what is the equation of that for a given x, for x as a variable. We use the Bayes rule. I go to the previous slide, and we'll obviously replace that by that. So now comes the question of learning the parameters of this surface. And here in the Bayes classification, we will first have to say, okay, what can we say about that? That's true. Wait, what can we say about that? What can we say about that? Any suggestion? What is this? This is the PDF of the features belonging to class 1. Give me things that you can hypothesize about that.
Gaussian distribution.
Yeah. Let's say, why not, that this is a Gaussian distribution. Why do you say that?
Because everything is Gaussian?
No. I don't think the marks that you will get in this course are Gaussians because they are bounded by 6 and by 0. Right? So wrong answer, no, sorry. Not everything in the life is Gaussian, right? But when you have accumulations of factors, by the famous rules, it comes to a Gaussian distribution. So if you have many factors influencing the value that you can have, and those values are random, la loi des grands nombres, how do you say in English, the rule of big numbers, I don't know, says that the limit distribution that you will get tends to be a Gaussian. And it's true that in nature, things are nicely Gaussian. I take again my example of small cats and big cats. What is a small cat? Well, it's a cat of that size. And the distribution of the possible heights for a small cat is from very small to reasonably big. And the distribution of the size for a big dog is from big but not that big to really big. You see what I mean? What an example. And this is recorded. Oh, gosh. Anyway. It's not totally stupid to say that things are randomly distributed with a Gaussian distribution. It's an hypothesis. Now I become serious. It's an hypothesis that you have to do when you have confidence that it is reasonably true. So if you don't know much about the distribution, it's not completely stupid to think for 2 minutes and say, yeah, it's Gaussian. So this is the hypothesis. But your problem can be described by other distributions. If the question is really like, my data are drawn from a uniform distribution, you will say that this has a uniform distribution. Uniform distribution is something for which you also have an easy equation. Huh? Or if you have something which is obviously always positive, like the absolute value of a random variable, this can have another distribution. But let's say, for the sake of simplicity, we are in a case where we can reasonably assume that that is Gaussian. Okay? So, and still we have to estimate the prior probability. But will you remember, this is also something we can estimate from the training set. So we will basically use our training set to estimate those distributions and the prior. What is a Gaussian? This is just a reminder. A Gaussian in 1D is characterized by its standard deviation and its mean. A Gaussian in L dimensions is characterized by its mean value in the feature space, in the space of L dimensions, so a vector somewhere in that space, and a covariance matrix, which gives you basically the variance and the covariance along the different axes and across the different axes. So you have a L dimensional mean value, the point somewhere in your feature space. In the 2D case, it was like you said, the mean of the cloud, and a covariance, which is an L by L matrix. And those things, if you receive a training set, you can estimate them. Because if you receive a training set, you take the points of class 1 and you calculate the mean, as you said, and then you take the function in MATLAB or in Python, cov, and we calculate the covariance matrix. So you can get them. This, assuming that the distribution is Gaussian. And there are ways to check whether the points that you receive nicely fit a Gaussian or not. But if you believe that the distribution is not Gaussian, take another expression for the distribution and find the parameters of that other expression that corresponds better to the reality. Yeah? But for here, we assume we have a Gaussian distribution. Okay, and we can have the estimators of the mean and the covariance. So now that we have that, we can move ahead. We can say, I want to estimate, I go back, I want to estimate for each class, where am I? The value of the PDF at point X multiplied by the prior, and you remember how we estimate the prior? We did that for the pixels. You have a training set. How can you estimate P of class 1 and P of class 2? You have a training set.
Number of points in class 1.
That's a good estimate. The appearance of the different classes in the training set. That's a good idea because it will tell you which one is more probable a priori. You have to be careful though. Can you give me an example where the number of points in the training set for each class will not be a good estimate of the priors? Very simple.
Not enough observation.
Not enough observation, so you really have too few estimations to really estimate. But remember, you ask your biologist to give you examples, in the case of my cells. What would be the danger?
For example, if you look for tumors in the brain or some cells or not tumors.
Yes? So there might be rare cases, that's what you mean? Yes? But even more dangerous. It's very probable that you will ask your biologist to show you 1,000 normal and 1,000 cancerous cells. It's very likely that you will ask him to give you 1,000 of each or 10,000 of each. Of course, in that case, you cannot estimate the prior based on that because you explicitly asked a number of examples. So this is valid if you ask a random sampling of the reality. If you ask your biologist to randomly sample cells and then to tell you which ones belong to what, then it's correct. So you have to have a random sampling and uniform sampling of your space to generate a training set in which you can estimate the proportions of each. This is just a parenthesis. But so let's assume now that from the training set you have been able to estimate all the parameters of the PDF and to estimate the prior. And let's come back to the idea of this is Gaussian. Now, the equation of my decision line, remember, we have to evaluate the equation of the decision line so that we can evaluate it whether it's positive or negative and then classify. Yeah? So now, this equation, I can write it easily in the case of Gaussians because Gaussians have the good idea to have an exponential there. So we have the clever idea to use my function f being what? A log, of course. And nicely, a log is monotonically increasing. Ha! So, it looks complicated, but it makes your life much simpler. Gi, the first term of my discriminant function, my decision line, Gi will be the log of this probability. The log of the posterior, which is the log of the product of the PDF and the prior. And now playing a little bit with the log, this is the log of the sum, because it's a product. And this is the log of an exponential. So, believe me and do it yourself after. If you put back the equation of a Gaussian in LD there, this is what you get. You basically cancel the E, and you get only the exponent, which is basically this, plus ln of this, plus the logarithm of that, or that here, which is constant, which contains only the estimate of your covariance matrix, which is a constant. Okay? So my GI for class I has this expression. And why make it simple when you can make it complicated? I write it again. I distribute, blah, blah, blah. And this is the equation. Now it looks very complicated, but it's not that complicated. The equation of my decision line is GI minus GJ equals 0. So that minus the same with a J equals 0. And that is the equation of the line separating two Gaussians in a L-dimensional space. A Gaussian is 2D is that, a Gaussian in 3D is that, a Gaussian in LD is something. But if you take two Gaussians with their own covariance and their own mean, their intersection is a line that has this equation, GI minus GJ equals 0. Now let's try to see what it is. Imagine, try to read this. What is x? X is your feature vector. Let's do it in 2D. Your feature vector in 2D is xy, or a1, a2 in the example. Let's say xy, xy, xy. So you have xy, sigma minus 1, so it's a 2 by 2 matrix, xy, plus something where you have xy, a matrix, and the mean, which is a constant, 2D vector constant. Here you have not x at all. This is a constant, a vector. Here you have x again, constant, constant. So basically, the equation of the discriminating function, the decision line, gi minus the same with the g equals 0, is basically a term where you will see something in x square, something in y square, something in xy, something in x, something in y. So a quadratic term, a linear term, degree 1 term, some constant, again some x and y, constant, constant, equals 0. So when I will write this discriminant function, the equation of the decision line, I will basically have an equation which is something x squared plus something y squared plus something xy plus something x plus something y plus a constant equals 0. That will be my equation. Does it sound familiar to you? Do you recognize some known curve in a 2D space in that case? It can be an ellipse. It can also be something else, but it can be an ellipse. What else? Parabola. In general, what? A curve of degree 2. The name is a quadric. So indeed, the equation of the intersection between two Gaussians can be a circle, can be an ellipsis, can be a parabola, can be a hyperbola. In general, it's sure that it is an equation corresponding to a polynomial of degree 2 equals 0. And a curve in the space that has an equation, second order polynomial equals 0, is called a quadric. Depending on the parameters, it can be a circle, it can be a parabola, it can be an ellipse, depending on the plus and minus, you remember. You remember that, huh? Depending on the sign of the coefficients of each term, it can be a parabola, an hyperbola, blah, blah. But still, it's a quadric. So first thing to learn, the intersection of two Gaussians is a quadric. Let me show you a few examples. So gi minus gj, gi minus gj equals 0, will always be a quadric for Gaussians. It's not any intersection, it's a quadric. Just let me show you an example visually. Do you see a first Gaussian here? You see it? And it's a round Gaussian, an isotropic Gaussian, a big Gaussian like that. Now let's say a small Gaussian. A very picky small Gaussian here. You see it? And the intersection between that one and another one situated at the same place but very large, the integral should be 1. So if mine one is narrow, it's high. And if the other one is wide, it's lower, obviously. What is the intersection? Obviously, it will be a circle, one of the isocurves of the two. Now, if one of them become an Gaussian, but an elongated Gaussian, and the other might be like that, the intersection might become an ellipsis. If they split away from each other, the intersection might be something like an hyperbola. So you see, depending on the position of the means, here we take examples with two different means, one here and one here. And we have Gaussians here and Gaussian here. And depending on the shape of those Gaussians around their mean, means depending on their covariance matrix, you might get an intersection which is a nice circle, an ellipsis, or if they move from each other and have strange shapes, and a hyperbola or a parabola. Depending on the parameters, that means depending on what you read here. But what is true is that it's a quadric. So, coming back to the examples of my cells at the beginning, we have decided to put the decision line as a straight line. It's a bit strange, because it seems that my two distributions are Gaussians. So the ideal intersection would probably not be the line, the straight line that we have defined. But maybe yes. Do you think that, so first, is it okay? Do you see what I mean here? The equation of the decision line, intersection between the two Gaussian distribution, in the most general case, and hyperquadric. Hyper means in any dimension, but a quadric. You will just have to evaluate the mean and the covariance of each class, use the parameters of those two estimates to calculate the parameters, the coefficients of this quadric, and then you have your line, so you have your classifier. You take this equation, it's a circle, it's a quadric, you evaluate it for your given point. If it's positive, it's class 1. If it's negative, it's class 2. And if it's 0, you are not lucky. Okay? So very, very simple. Very simple. But optimal. This classifier that you can build is the one that will commit the smallest number of errors. It's the Bayesian classifier. So this very simple classifier, estimate the parameters of a quadric and calculate the value of that quadric, the sign of that quadric for a given point, is the best classifier in the world. I used to say it's the Rolls-Royce of classifiers. Now I say it's the Tesla of classifiers. Where is it? Not here today? Too bad.
Still assuming your hypothesis on the data are correct.
Still assuming that your hypothesis is right. Assuming that the distribution is indeed Gaussian. And you have to know it. If your data are not Gaussian and you take the hypothesis that it is Gaussian and you estimate the quadrics, the mean and the covariance of a distribution that you received from, that you estimate from a training set, and if it appears that the data were not Gaussian, you will still have a decision line, you will still have a classifier, probably not that bad, but not optimal. It could be completely wrong. But if you know that your data follow a certain distribution, okay, it's a lot of information. But if you know, you should really use that. Because this is the Tesla of the classifiers. Now, let's take this equation again. That one. So the equation is gi minus gj equals 0. gi being this, gj being the same with a j. What we did at the beginning with your colleague here is to draw a line, and you also, by the way. A straight line, a linear classifier. Can you see a particular case of that, and I will not show you where, which will actually make my hyperquadric an hyperplane, which will make my quadric a linear equation. Just to see if you see. This is a degeneration of a second-order polynomial. A line is a first-order polynomial, a line, is a degeneration of a second-order polynomial. What is the condition for my optimal Bayesian Tesla classifier to be a linear classifier? And you had the right to give the answer.
If the two have the same variance, so the sigma I will disappear by the difference.
The only parameter that I have here for the quadratic term is sigma I. When I write gi minus gj equals 0, this second-order term will disappear if gi equals gj. If sigma I equals sigma j. So, when we drew this line between the two classes, it was actually probably the right shape. I still don't say why it was there in the middle. But it was probably the right shape, a line, if we assume that the two classes have the same distribution, means Gaussian with the same covariance matrix. And this is not completely stupid. If you have small dogs and big dogs, they don't have the same mean by definition. Oh, dogs now, not cats. But it's not completely stupid to say that the range is pretty much the same. Well, might not be the good example, but you see what I mean. You hypothesize, or you have realistic reasons to think that the variance in 1D, the covariance in LD, are the same for the different classes. Why not? And if you can do this hypothesis, what you know is that the best classifier in the world is a line. Fantastic, no? And you just have to estimate the equation of that line, that plane, that hyperplane, depending on dimension. Okay? And this is what I have here. If the different sigmas are the same, Not the mean. If the mean are the same and the sigma are the same, the distribution are the same, you cannot distinguish them. But if the shape of the distributions are the same, then what you know is that your discriminating function is actually a linear function, and so gi minus gj is a linear equation. Gi minus gj equals 0 is a linear expression, where the parameters can be easily calculated by estimating the mean and the covariance of the different classes. The covariance being the same, I don't have in this anymore, and the means being different, I keep them, of course. So you estimate wi for each class, and you also estimate wi0 for each class, which is where you group all the constant terms, and you are done. And now we can look at what it really means. Because now, gi is this, in the case. Now let's take an even more special case. The case where, on top of being the same, they are diagonal with the same elements on the diagonal. So that means that my Gaussians are isotropic. All the axes have the same range, because you normalized your data, for instance. Now, in that case, all the sigmas, which are already all the same, have that shape. So my gi, you can trust me and you can verify if you wish, the gi will come up with this simple expression. You have the sigma 1, the sigma I, the sigma to the power of minus 1, which in the special case just means 1 over sigma squared. You have your different means, and you have the constant, and the constants, they are the same as before. And so in that specific case, my line is gi minus gg equals 0, which is this. And again, in identifying correctly the different terms, you have w being, you write that gi minus gj, and you will easily see that you have a first term here, w, which is that. You will have here mu I minus mu j, and you have an x0, which is that. Again, I show you what gi should be in the most general case. Gi in the most general case, this term will disappear. You will have something here. You will have that. You have the priors and so on. If you do all those assumptions, the sigmas are the same and they are diagonal with the same elements on the diagonal. This ends up by this equation. And now let's have a look at that, and we will have a first break. This is the equation of the best line in the world that will separate my two classes in those hypotheses. This line, obviously, passes through x0, because obviously the value of the line at x0 is 0. What is x0? It's that term. We'll come to it. And obviously, that line is such that for each point of the line, the vector joining the point of the line to the center is, the point of the line to x0 is perpendicular to a vector which is called w, because the dot product is 0. This is any vector on the line. The dot product with w is 0. That means that the line is perpendicular to w. What is w? The vector joining the two centers. So, in the specific case of Gaussian distributions with the same covariance matrix, this covariance matrix being a bit special, then the best classifier in the world is a line that is perpendicular to the line of the centers, and your colleague was right. But only in that specific case. And moreover, he was even more right, because that point is actually what? Well, it's actually, forget that, don't look at that. It's actually the mean between the centers. So you were very good. Huh? Cool, huh? Why do I ignore that? This becomes 0, in which case? These additional terms become 0 in which case? Easy case. When the two priors are the same. We mentioned that. Huh? The two probabilities of the classes are the same. Then, indeed, the best classifier in the world is the linear classifier perpendicular to the line of the centers going through the middle. This is very simple classifier that you estimate by just picking the two centers, drawing a line. If it's in LD, you pick the centers and you draw a plane or a hyperplane. This is the best in the world. But only in the hypothesis of Gaussian distributions with the same covariance. This covariance being a bit special, and the two classes have the same prior probability. So he was right, but you see in a very small number of cases. But it's not totally stupid. And if you don't know much, it's not a bad classifier. What does this term say? What does it say? It says that if the priors are the same, it's really the middle. But if the priors are not the same, the point where you position your line will basically move away from the most probable. Away, because of the minus, from the most probable, which is true. If you have a class that is highly probable, I was wrong at the beginning, I think when I explained that at the beginning of the course. When you have a class that is highly probable and a class that is not very probable, the separation should be away from the most probable because it should include more points because it's more probable. Right? So the points should be biased towards that one. And the bias is really that. And it's probable that I gave the wrong explanation intuitively at the beginning. You have to watch that again in the movie. Okay? So now we understand what is a Gaussian classifier, a Bayesian classifier, sorry. We understand how to build it and what happens when the distributions are Gaussians with or without specific cases. Just before breaking, what is next? Just before breaking, so when you receive a classification problem, you receive a training set with the labels, so you are in a supervised case. You have to wonder whether you can set a realistic hypothesis on the distribution, whatever it is. If you have this hypothesis that is correct, or reasonably correct, you take the equation of the distribution that you assume. From the data, you estimate the parameters of that distribution, not necessarily a Gaussian. It can be any. There are ways, I will not give them here, expectation maximization, maximum likelihood estimates, I would say, to estimate the parameters of a distribution knowing data. Maximum likelihood is the right term. You get the parameters, Gaussian or not, whatever your hypothesis is. You write it down, gi minus gj, and this is the equation of your line. You give a new point, you receive a new point, you evaluate the sign of this expression, positive is class 1, negative is class 2. This is the best classifier in the world. And it simplifies down to that in some specific cases. But it's the best. Why do we machine learning? Why do we do machine learning? Well, because we don't know the distributions. When you do a neural network, it's because you don't know the distributions. But if you would know, certainly you would not choose to train a neural network. You would do that. Yep? Yep. Questions? Comments? Yes, please.
Yeah, but machine learning, if we, for example, if we apply a simple perceptron, that require in the last term that it's a Gaussian distribution?
It doesn't require. It will become optimal if it is a Gaussian classification. It never requires. You do what you want, but it will give you better results if the function that you will learn with this perceptron actually correspond to the optimal theoretical distribution. But when you do data-driven classification, you basically don't know. Again, if you know that it is Gaussian, don't train a perceptron. Just estimate the line. So what you say is actually a little bit the opposite. When you train a perceptron, you don't assume that it is Gaussian. When you train a perceptron, you know that it will do something which will be good if you are lucky because it was Gaussian. But basically you don't know, otherwise you would do a Bayesian classification. But you cross the fingers. That's the truth. You cross the fingers that you are close to something which is optimal. But you don't know, otherwise you would do the optimal one directly. Okay? Questions, comments? That's okay? So let's have a first break. Okay, welcome back. So just before starting again, let me say again the tentative schedule for the rest of the semester for those of you who arrived after the first hour. So lecture today, lab next week, office hours of the assistants for the previous lab during the week as last week. We'll have another office hour after. Then the special project will start, so please come on that day. Yes, please do come. Please do come here on that day at 8:15 because we'll start immediately, like a lab. But please do come here because we'll have the introduction. And then you will do what you want. Yes, just one moment. And then we'll have the interviews, and I will send by Monday a doodle with large slots, like 3-hour slots, allowing you to choose between that, but also 2 other days, Thursdays afternoon and Fridays afternoon for some of them. Again, I repeat, please indicate all the possibilities for you because it will simplify my life when I will have to really assign. So play fairly. Do not block one single slot for all of you. If you have another course on Friday morning, really consider whether you can skip just once to come or 10 minutes to come to the interview. And then you make you available at that slot, if it's possible. Okay? Then we will have the final project. And for that one, I will not have other time slots. So you have to make you available on June 1st morning. We can see when, but that will be a whole morning. And I will ask each group to be there for their presentation, obviously, their demo, the previous one, and the next one. So you have to stay something like half an hour or so, a bit more. It's also for, competing a little bit. Yeah, that's it. You had a question.
Just organizational type for the introduction and special project can be a little bit organized. This is one TA told us at 10.
Say it again.
If it's a Friday, can you repeat something at 10?
Yeah. So what is convenient for you? We are happy if you prefer doing only that introductory session later in the morning, if it's better for you. Yes. But I will not have 3 introductory sessions. Huh? So do you think, what time do you arrive? Those guys taking the computer vision? 10? So let's have it at 10:15 for all of you? Fair? 10:15 for the introductory session on the robot project. 10:15 on May 11.
It would just be good to have it at 8 so we have all the morning to work.
2 of them. One at 8:15, one at 10:15. I don't care, I will not be here anyway. 8:15 and again 10:15. Done deal? Then you really have to give me a good evaluation for my course, guys. Okay? We'll do an effort, huh? No, not joking. The evaluations have started, so please do complete the evaluations of the course. Give your comments. Please give your comments. Be constructive. I don't want you to be always positive. I just want to be always constructive. Saying that it's really bullshit is not constructive. Say what we could improve. You have to keep in mind that this year was a very exceptional first time that we had people from other sections than EE because of the interest in data science, and also people in EE taking the courses outside EE. So we had this conflict of agenda, which is not our fault. So we try to cope with that when we discovered that. So please do not blame us too much for that. We cannot control. We make the schedule of the students optimal for those who stay within their section. Okay? And so I hope you appreciate, or at least you acknowledge, that we try to cope with your needs as much as we could. This is off the record, not totally, but still. Okay, back to the course. So what do we have? We now have a complete analytical expression for the optimal classifier, Bayesian classifier in case of Gaussian classification. And at the end of the day, for some specific cases that we mentioned before, this classifier is extremely simple. So simple that actually, as you see, that's what we said, it can be just the line perpendicular to the two means, to the line of the two means, by the middle. So simple. In that case, building a classifier is just stupidly simple. Because if you get a new point, what is the only thing that you have to calculate? In that case. Huh? How far it is from the line, or even simpler? From each mean or its mean? And I would say from each mean. Because you see, this line is the line perpendicular to that. So if you do a little bit of simple Euclidean geometry, this is the line at equal distance between the two centers. So a point is on one side of the line if its Euclidean distance to one center is smaller than the Euclidean distance to the other. So in that specific case where the optimal separation line is this one, the classifier is just, you take the point, you calculate the Euclidean distance to mu1, Euclidean distance to mu2, and you're done. You don't even have to calculate the line. And this is Euclidean distance classification. And this is indeed the best classifier in those cases. Shall I repeat it again? Yes, I will. It's funny. It's the best classifier, optimal, Tesla classifier, when the distributions are Gaussians with the same covariance. This covariance matrix being isotropic, and the priors are the same. And then you have that. Now what happens if the covariance matrices are not nicely shaped, are not isotropic? They are like that. Still, we are in the Gaussian case. The covariance matrices are the same, and the priors are the same, but the covariance matrix is not roundish. It's not isotropic. It's not the diagonal. It has some kind of a principal axes that are not the main axis. Then obviously in that case, I don't know if you can see it, if I draw the perpendicular to the line, it will be that. Right? The perpendicular to that line roughly is that one. But obviously, looking at the shapes, the correct line is something like that. Right? So basically what it means is that in the case of a Bayesian classifier with Gaussian classifier, where the covariance matrices are not diagonal, then it's basically the same. It's a line which passes through the middle, but it's just tilted as compared to the perpendicular. And if you write all the equations that we wrote before, you will realize that the actual equation is still a line, good news. It still goes to x0, which is still there with the same bias towards the less probable class. But the vector here, which is the vector giving me the perpendicular to what I'm considering my line, the line is perpendicular to that. If you write exactly the same equations, you will realize that W is actually a sigma minus 1 in front. And you remember in the vector space, having a vector pre-multiplied by a matrix will basically turn the vector. It's a transformation, a defined transformation, rotation translation. Right? So basically, this explains why this axis is actually tilted. Tilted based on the sigma minus 1. So it's very simple. Now you can still do distance-based classification with that. Remember, you can do distance-based classification by the Euclidean distance between the point and the centers in the very specific case. But if you rewrite everything, you will easily see that if you receive a new point, you can still classify it by calculating the distance between the two centers in the case where the covariance matrix is not that simple. You just have to adapt the definition of the distance. You just have to consider a distance which is not the Euclidean distance anymore, but it's a Euclidean distance where you add somewhere the sigma minus 1 in the middle. So instead of calculating x minus mu I times x minus mu I, which is the square root of which is the Euclidean distance, well, square root, you basically add sigma minus 1 in the middle, and then the rest remains valid. This line is the line, this line is the line that is at, for each point, is at equal distance of the two centers if you consider the notion of distance, which is not the Euclidean, but that one. And this has a complicated name, Mahalanobis. So this is very usual when you receive a data set and you say, okay, I don't know much, so I will say it's Gaussian. And I don't know much, so I will say that the covariances are the same. And I don't know much, but they don't look isotropic. It seems that there is an axis that is bigger than another. And I don't know much, but I will assume that my classes are equiprobable. Then you simply build a classifier by calculating the covariance of the data. They are the same, but you calculate one of them. And then you say, okay, my classifier is just, I take a point and I measure the distance to the centers by the Mahalanobis distance. This is very usual. And actually, there is no risk because if you were lucky and actually the covariance matrices were diagonal, this will be equivalent to that. The classifiers will be equivalent. The distance will be just scaled by that, but which one is bigger remains valid. Okay? Clear? So this is quite long, but I really wanted in this course to go in the details of that because it is extremely nice to see how to build an optimal classifier and how simple it can be in specific cases. And simple doesn't mean suboptimal. Simple can be optimal in some cases. And that's really what I want you to remember. This is only true, as we said before, if your data come from the actual distribution that you assume. In other cases, you will have to guess. So now, let's move to other algorithms. We stop with the Gaussian Bayesian classifiers, and we will see what you can do if you cannot have a good estimate of the distributions. You cannot reasonably assume the shape of the distribution. And I want first to see a very simple but extremely popular algorithm, which is called KNN. Students sometimes have difficulties to re-explain when we have the interviews what a KNN is. It's extremely simple. So just listen and you will see. If you remember what KNN means, it means K nearest neighbors. And the title says everything. The rule is extremely simple. You have a training set. You receive tons of points with their correct label placed in the feature space where they are. And classifying a new point by the KNN algorithm is just, you take the point where it is in the feature space, and you look at the K nearest neighbors. So you look in the training set, which are the K is a value, 5. The 5 nearest neighbors. So you find 5 points that are the closest to your point, and for each of them you know the correct classification because they are part of the training set. And you just look among those 5, what is the class that is most represented? If in those 5 points you have 3 points from class 1 and 2 points from class 2, you say my point belongs to class 1. That's it. Simpler than that you cannot. Many advantages. First, you don't do any assumption on the distribution. You don't. You can do that how you want. Second, it gives very good performances. And there is proof of that. I will come to that. Drawback, you have to have all your training set in memory, and you have each time to calculate the K nearest to your point, which is time consuming. There are tricks, but not that many. You still have somehow to go through all the points and see which one are closest. There are tricks playing with distance maps, you know what it is, to find the closest. But since you have to find the k closest, it's not that easy. Yeah.
You also have to know k.
That's where I wanted to come, obviously. Thanks. You have to know k. You have to choose k. K is the number of points you consider. And you have the choice. And there is a nice property of k and n which shows its beauty. First, it's extremely simple, but still, it gives a probability of error which is smaller than twice the Bayesian probability of error. It is not worse than twice the probability that you would, the probability of error that you would do if you would know the exact probability PDFs. You don't. But if you would know, you would do that. If you would know the probability, the PDFs, you will do a Bayesian classifier. It will give a certain probability of error, the area under the curve, you remember? With a 1 and n, you choose the nearest neighbor. You are not that bad. You only do twice more errors, which is not that bad, huh? For a simplistic classifier. And even more, if you increase k, this exponentially goes down, asymptotically goes down to PE, the best in the world, the Tesla classifier. Strange, huh? Why do you say? You're right, please.
Because in the case where k equals n, the number of samples.
Aha. That's the trick. Of course, you're already going to the trick. Let's take one step back. Intuitively, when you see that, you would say, haha, it's simple. I will take k as big as I can. Take k infinity, and you're done. First, it will take an infinite time, but that's not a problem. Second, the maximum k you can take is the k corresponding to the size of your training set, obviously. Because you want to find the k nearest neighbor, your training set has n value, n points, so the maximum you can do is to take all of them, right? But that doesn't work. And you see why. That doesn't work because I take a point. I have a training set with 500 points of class 1 and 600 points of class 2. Nicely mixed, 500, 600. And I do a 1100 n classifier, 600 plus 500. So I take a point, I look at its 1100 neighbors, and I choose the class that is most represented. It will always be class 2. That's what I said? Yeah. Then I take another point. I take its 1100 neighbors, class 2. So if you take k too big, you will definitely always take the same decision, which is the class that is most represented in your training set, which is stupid. So this is the trick. You have to take k very big, but not too big. I like this rule. K has to remain significantly smaller than the size of your training set, but still quite big. So the right way to do it, actually, is to estimate k based on your training set. What you actually do is to take your training set. You take 1 point in your training set. You actually know its value because it's class, so it's in the training set. But you act like if you don't know it. You classify it by a k and then k being 1. And you do that for all the points, and you calculate how many errors you commit. Then you do that for 3. Of course, I take an odd number. 3, 5, and so on. And you increase, and you see how your error rate decreases. And then at some point, it will decreases because of the bias with the training set. And typically, because it's computationally expensive to do a high k classification, you have 5, 10, 11 k classification. But you learn from the data this superparameter by cross-validation. Yeah?
If samples from the different classes are the same, for example, 500, 500.
You are not lucky. No, if they are the same, that's okay.
That's okay, we can increase the...
Anyway, you will never increase the k too big, because otherwise it will always say, if you take a k of 1000, it will always say, I don't know, which is not a good information. But if you take it smaller, it will look around, and what it does actually, it estimates locally the distributions. By choosing the most probable in a circle around your point, in a sphere around your point, it basically estimates what is the proportion locally of your two distributions and where is the separation. That's what it does. But it does it locally.
For example, 1,000 sample
Depends on how they are spread in the space. I cannot tell you. It very depends on the case. But typically we do 10, 11, 12, 13 K classification. That's already not bad. And so you can do that. And if you are in a 2D space here, I will not take this example again, but it's an example of gray values in an MRI. You can basically do a KNN classifier for different classes and get very nice results in the classification of this problem of discovering multiple sclerosis in the brain. Doesn't really matter. Okay? So, let's move to the last part of this course, almost. Now, we will move now from Bayesian. Well, we have seen the KNN, but that was a parenthesis. But Bayesian, so optimal statistical classification, for which we have to do a lot of hypotheses. And now we move to data-driven. So I want to finish this course by a quick introduction to neural networks. Quick. And I start from the point of the linear classifier. And then we come to the idea of your colleague here. Remember, choose a line and then find a line that minimizes the number of errors. That was your idea. That's exactly what we will say. A linear classifier is a linear. Good. Huh? So you hypothesize that the decision line that you want to take is a line, is a straight line, a linear. This is an hypothesis. Is it a good or a bad? I don't know. But a very good rule is when you don't know, don't make too many assumptions. When you don't have enough data, use simple models. That's a very general rule. You don't have enough data, don't use a very highly parametric curve. Make it simple. That's a very general rule. So, in many cases, you will have a problem of classification and you will say, I don't know much, so I will say, I will learn a linear classifier. I will learn what is the best line, exactly what he said. I know that the best line, if I refer to the Gaussian case, the best line would be a good idea in some cases. So that was your comment. If you want to train a linear classifier, and by chance the data correspond to Gaussian, blah, 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 then you are very lucky and the training that you will do will actually find a very good classifier. And if you don't know, you just say, I will try. And that's it. So let's say you want really to train from the data the values of the parameters here, not estimate them from the training by doing a hypothesis of the distribution, but really finding the values that on the training set will commit the smallest number of errors. So minimizing a loss function. So you basically have to find those parameters. I group there in one vector where I include the slope and the bias, the zero value. But I have to find the parameters of that line in the space. And I know that if I find the right line for a given point which is of equal probability of belonging to both, no, for a point that where I cannot decide, the equation will be zero because that's the equation of my decision line. And I know that for the points that are on class 1, this expression will be positive, and on class 2, I have to say it correctly, yes, for the points that belong to class 1, this expression will be positive, has to be positive, and for the points of class 2, this expression has to be negative when I will find the optimal parameters. So my goal is to find that such that the number of errors is minimal. And what is an error? An error will be, for a given W, an error will be a negative value for a point that I know belongs to class 1, or a positive value for a point that I know belongs to class 2. That will be an error. Right? I repeat. An error for a given line, a point misclassified will be a point for which, for that line, W time that point will be negative while I know that the point is in class 1, because I train, I know the value, or will be positive when I know that it is in class 2. Yes? Is that clear? Yes? So, my objective now is to find what is the best W such that I will have the smallest negative values for the points of class 1 and the smallest positive values, smallest number of positive values for the class 2. That's how I measure my error. So my loss function, my measure of the error, can simply be the sum for all the points that are not correctly classified of their W time x, knowing that they will be from the wrong sign. And what is the little delta is just to switch, because the idea is to say, I will take a point. I will take all the points that are misclassified with a given W, with a given line. And I will add the errors. I will add those values which are wrong. If the point is in class 2, it's misclassified in class 1, so this will be positive. And I will take this as a penalty. This positive value should be negative, so I increase my penalty. I sum W times x, which is positive, and the bigger it will be, the worse the classifier will be. And same for the points that are misclassified, that are in class 1, but accidentally classified in class 2. This will actually be negative, and I will take this value, change its sign, because it's negative, otherwise it would decrease my penalty, change its sign, and add it to the penalty. So my penalty, my cost function, is the sum of all those wrong values, making sure that they are all positive to sum up, so that when I will minimize, I will find the right solution. So this is the penalty, the cost function, the sum for all the misclassified points of their actual value for a given W, just with a sign change if needed. And now I just have to find what is the value of W that will minimize this cost function. And when I find the W that will minimize this cost function, I will have found my best linear classifier based on my data. At least the one that minimizes my cost function. And I do that by a simple gradient descent. You remember what a gradient descent is? You start from something, and you iterate on your unknown by going down the gradient of your cost function. And my cost function being that, its gradient with respect to W is extremely simple. You just add the values of the points, the values of your feature, with the correct weight, the correct sign. So it's terribly simple. It's a linear expression with respect to x. So the gradient of this is the sum of the values of the feature vectors, the sum of the feature vectors that are wrongly classified, some of them having their sign changed. So you basically iterate like that. And what happens is that you initialize, and then you go down the gradient. And this is exactly what your colleague explained. You do that, and you iterate until convergence. You have your data set, 2 classes, as you can see, and you have your first estimate, random estimate of your classifier. Boom. This is my line, W0, W first one. Okay, that's not too bad, but bad luck. 2 points are misclassified. Your gradient descent algorithm will say, for those 2 points, calculate their sum, somewhere here, and update the value of your weight by a portion of that. You know this learning rate. It just has to decrease. It has to be small and decrease. And you update the value of your weight by modifying the W by a fraction of the error. And it gives you another. And at the beginning, you start with a big rho, a big learning rate. So, too much. That's okay, because here now you have those 3 points wrong. So you update again. A little bit less because, okay, you were a bit energetic. Ah, better. 1 wrong here, 3 wrong here. Obviously now, this will shift a little bit your line. Aha, not too bad. 1 and 1. Yep, 1 and 2, haha, too bad. 1 and 1, we're coming. 1. Yeah, 0. Yeah, 0. Yeah, and that's it. This algorithm will stop because from this training set, there is no error anymore. So the algorithm will stop. This is a training algorithm for what is a very simple neural network. Because calculating a linear classifier, which means take your feature vector, multiply it by a weight, calculate the sum and remove or add a bias, which is exactly the equation of my line. Huh? This is exactly the equation of my line. I take the point, I multiply by weight, and I remove a bias. Can be drawn as, if you don't have good eyes, looks like a neuron. This is a neuron. And this algorithm, the linear neural network, is called a perceptron, a single-layer perceptron, reference to the perceptive neural networks, the perceptive neurons. And so this algorithm is called the perceptron algorithm. It trains a perceptron, a single-layer classifier, which allows you to train a line. Now, I just want to make a comment which refers to your ID, your very initial ID. Is that a good classifier? Well, it's not bad. As far as I can see from the training set, on the training set it doesn't commit any error, which is not a very good, not a very powerful criterion still. You say no. Can I just ask you to say why you think it's not a good one? Because this was her idea at the end.
Because intuitively, I will take a line which maximizes the distance to the nearest point.
Yeah, there is a kind of a band there. And it's a pity that this line is kind of too close to that and too close to that over here. It would probably better position in the middle of the band, right? Because then what we say is that it would generalize better. Imagine that you generate another point in your training set which is just here. Bad luck. It will be wrongly classified. While if you put your line in the middle of the band between the two classes, more points nicely drawn from the same distribution will kind of remain still on the right side. There is here what we call a margin, exactly. And classifiers can be biased towards, you can train a linear classifier that will actually not minimize the number of errors, but maximize the margin being the distance between the line and the closest training point. And when you do that, the closest training points are called the support vectors, and the machine that you will train is called a support vector machine, an SVM, very famous classifier. But it's very much, and the linear SVM is very much like this one, except that you have a penalty which allows you to maximize the margin. I will not give the explanation, but that's where it comes from. And you have linear SVM that works great. Okay? And they are nonlinear, I will not see them here. Now, let's move ahead. This is fine. You can train a linear classifier. Again, if you don't know much about your problem, you don't have so much data, don't make a complicated model. Make a simple model, and a linear model is not a bad idea. And it's easy to see here. This is a training set, 2 classes, with kind of very few training points. Imagine what would happen if I use a more complicated model. Because you can say, instead of fitting a line, you can fit a straight line, you can fit a line with more parameters which can handle more complicated shapes. second order polynomial, third order polynomial, complicated parametric expression. That's true. It will probably give you a shape that better fits your data. But look, imagine you want to train a very complicated, many parameters model on this data set. How many? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 15, 20 points I have. Let's imagine that you are crazy and you say, instead of having a model with 2 parameters in 2D, so 4 values, slope and origin, you train a model with 20 parameters. Because you say, it will be certainly better because it will better capture the reality. What will happen is that your model will be so complicated with respect to your data points that you will basically fit 20 unknowns with 20 values. So the model will basically do that. It will really turn around your data points and stick to the data points so much that it will be perfect on your training points, on your few training points, but totally wrong as soon as you give another one. Because it will create classes that are so nicely fitted to your individual training points that it will do what is called, thank you, overfitting for the recording. Overfitting. But this is the reality. I hope you see how intuitive it can be. We all know what overfitting is, but you really see it here. You see why I like this lecture. Linear is a good idea, but you can do more. And I will go quickly because it's obvious. And I'll take a strange example. You will certainly wonder why I take this example. The reason is simple. Why to make it simple when we can make it complicated? This is a 2D feature space. And I want to classify, one class is here and another class is here. And to make it complicated, this corresponds to an operator which is the OR operator in the binary logic. Why? Just to make it complicated. And that, implementing an OR, that means classifying those 3 points in class A, which is 1, and this point in class B, which is obviously 0, can be done with a single layer perceptron. You take the values, you multiply by 1, you sum, and you see how it compares to minus a half, being positive or negative, and you get your solution. So this is the single layer implementation of that operator. Now take another classification problem where the classes are not linearly separable. Just to make it complicated, let's take a Boolean expression that takes the XOR. And XOR has 1 here and 0s here. Right? So there is a class which is here, another class which is split in 2. Obviously, you cannot realize that with a single perceptron. But what you can easily do is to say, okay, I will build a first one which will discriminate that class from the rest of the world, another one here that will discriminate that class from that class, and then I will say, if it's on the right of 1 and on the left of 2, it's that, otherwise it's the other. So what I'm doing here is very simple. I'm actually taking the perceptron I had before, with the 1 and the 1, which is that line. I built another one which will implement that one. It seems that it will be also 1 and 1, but we compare it to minus 3 halves. That will implement it, that one. And then I will do another perceptron which will combine the 2. I am on the left on the one and on the right on the other. And, so I have an operation here which implements an AND operation. And by doing a 2-layer perceptron, I can implement a more complicated series of decision lines, the decision regions. Yeah? So that's really the intuition. Again, it was not just for the beauty of making it complicated. The idea of doing a multi-layer perceptron is to combine linear classifications. With a single layer, you do linear classification. Combining the decisions of several linear classifications makes it more flexible, and that's why we come to 2-layer perceptrons. And then, with that, you can do things like that. With a 2-layer perceptron, you can do regions like that. So on the left of the one and on the right on the other. on the left of that one and on the right of the other. You can do regions like that shape. And if you want to do more, you can combine comparisons of several of those regions. You add another layer, and you come to a 3-layer perceptron, an MLP, multi-layer perceptron, and then you can build very complicated regions by training the parameters. Of course, in the case of my XOR and 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 OR, I know the weights, but you can train them. You can learn them from the data. And so I will not say much more about machine learning, except that basically what will happen is that you will build a multi-layer perceptron. The unknown will be the weights and the bias that you have to put on each node. And then you learn them by a gradient descent, very much like what we did for the single layer. You have a cost function, which is the number of errors you create. You take an example, you classify it, it commits an error, or not. If it's correct, you are happy. If it's wrong, you update the weight by gradient descent of the cost function. And you do that for each of your training points, even several times for each training point. And by doing that, by gradient descent, you basically train your network. The only criterion that you have to have in your network to be able to do that is to be able to calculate the gradient of the cost function. And here, if you recognize, in all those cases, at the end of the network, you say whether it's bigger or not than a threshold. So you have a step function on there as an output. Minus, positive or negative. Bigger or smaller than a half. So minus 1/2 would be positive or negative. That is not differentiable. So that's why the actual neural networks have an output function, an activation function at the output of each neuron, which is not actually a step function, which would be, is it positive or negative? But it's a continuous, mainly differentiable approximation of the step functions, which allows to really calculate what is the cost function as the sum of the errors of the different layers, each of them activated not by positive or negative, not by a sign, but by an approximation of the sign. And then you have an expression that you can differentiate. And that's why we have a sigmoid there, which allows you to have boundaries which are not straight lines, but smooth lines. But the main reason is that my error, remember the error of the linear? The sum of the delta times x? Well, if you have multiple layers, it would be the sum of the delta times x and the sign of that enter test blah, blah. That would not be differentiable. So it's the sigmoid of the error each time. And then you calculate that, and you calculate the error, and you update your weights by gradient descent. And the algorithm is very famous backpropagation algorithm. You have a reference of the very old but very nice paper of Richard Lippmann. And that's it. That's it. Now, why are we talking about deep networks today? Deep networks have been around for, do you know when they were invented? Well, I say something where I don't know the answer, so it's a danger. Do you think that have been invented very recently, or they are very old? They're actually very old. But they never appeared. They were invented by famous guys today. Yann Lequin, French. People say Lequin, but it's Yann Lequin. It's a British guy, Breton. By Hilton and by Joshua Bengio. And it was invented extremely early. But deep networks are the expansion of that with more layers. So many more variables. So they can handle very complicated cases, but to avoid overfitting, you need large amounts of data. And so they are becoming popular now because of Facebook and Google. Really because of that. And other companies, but basically Jan is a consultant for I don't remember which one, but anyway, Facebook. Yeah? And so basically it's because of that. And now we realize that indeed it can be extremely powerful if you have enough data. And what those deep networks do is nothing else than that, but with more parameters. And if you have more data, you can do fancy things. You can actually have, and I will not give you a course on deep networks, but the famous convolutional neural networks. Have you heard about CNNs? Convolutional neural networks. They are neural networks where you learn all the parameters from the data, they implement a classification, but you have so much data that you can have a first part of the layer where you don't spend your time finding the right features. Instead of finding the features that describe your 0 and 1 like in the lab, you just say, I will learn the feature extractor. I will just take my image, and instead of implementing a Fourier descriptor that you choose yourself, you put a series of layers with enough parameters such that the system will learn by itself which filter, which might not be a Fourier filter, maybe another one, but it will learn. And so the first layer of a CNN are just convolutional masks, linear masks, but you don't know the weights of the mask. You don't know the value of the mask. It's learned from the data. And the second part is typically an MLP, typically that. And altogether, it makes a deep network where the first layer learn the features to extract, and the second part of the layers, classify them. But everything is learned from the data. But it doesn't change anything. It's still a deep network, and you're still training by propagation, except that you load TensorFlow and it's implemented for you. But it's okay. And in the lab, next week, this is exactly what you will do. You will use a deep network, not that deep. But instead of extracting Fourier descriptor, and I hope you realized in the lab that when you have to classify zeros and ones, it's like kind of okay to have two features. But as soon as you put the 3 and the 4 or the 2 and the 3 on the picture, it becomes a mess. Instead of trying to invent what would be the right features, you will let the system do it for you. You will directly enter the picture, the features of the pixels. And then they will be pre-processed by the first layers and then classified. And you will train a deep network yourself on the MNIST, the reference database, for character recognition. But I want you to realize that if by chance you would be able to estimate the distribution of the pixels that correspond to class 1, which is not feasible, obviously, you would probably do a Bayesian classifier instead of training a deep network. And I also want you to realize that a deep network is the deep version of a single layer perceptron, which is only a gradient descent on a cost function, which is a good approximation of a Bayesian classifier when the classes are Gaussians. Machine learning is basically statistics. That's why if you take the courses in machine learning, probably you start with serious statistics, hopefully. At least that's why I start with that in very general terms. Okay? Do you agree to finish? I need another 10 minutes. We do like usual? We continue? Questions or comments on that? So deep networks are interesting, but not magic. You can overfit them very easily. What is becoming very strange, by the way, is that deep networks are very famous, but when you want to use them, most of the time you reuse an already trained network, and you just train the last layer. So it's not that deep anymore because you don't train the rest. You believe that people have trained that. But at the end of the day, it doesn't change much if you use Fourier or Lequin features, if you see what I mean. They have been trained on the data, but not on your data. So you trust that they are the good features. Very much like you trust that the Fourier descriptors are the good features. They have been trained on other data that kind of nicely represent natural scenes, because most of the time those pre-trained networks that you will see, that like ImageNet, are trained on natural images. And if you want to use them on something else and you don't have enough data to retrain the whole network, so you want a pre-trained network, you just trust that this will apply to your problem. So it's not that deep. Huh? I like deep networks like everybody. I mean, our job has been killed by deep networks, so I'm sure I like them. But specifically, I want to, this is a joke, what I just said, because there was a trend like that. when deep networks became very popular, image processing guys said we will be jobless, we will be fired. And we discovered that it's not true because in real problems, first, you never have enough data. Second, if you have some data, you will still use a pre-trained network, so you have to understand what you do. And at the end of the day, probably you will do better if you do a Bayesian classifier when you don't have enough data. So keep in mind that you don't have to use black boxes. You have to understand the problem and do the right choice. So I think we're still useful. Okay? And that was also the outcome of a conference we had at EPFL with SMEs, with small companies. And it was about deep networks and big data. And they all said, that's beautiful, but we are not Google and Facebook. We don't have enough data. And the answer was, okay, good, come to us. But that's true. You have to know everything about image processing, otherwise you do stupid things. That's it. Let's move to unsupervised, and let's finish by unsupervised. We have a training set. In this case now, we move to a case where we can collect data, but they are not labeled. They are just there. And you can kind of visualize them. Of course, they live in a high-dimensional space, so you cannot visualize. But you kind of imagine that if they correspond to reality and the features that you have used are not completely stupid, your features will live in a space where, even if you don't know which class they belong to, it's very likely that the points of one class will cluster in one part and the other will cluster in another part. You don't know exactly which one is which, but you can reasonably trust that they cluster in the feature space. And so to do an unsupervised training and build a classifier from non-labeled data, you just have to identify those clusters, and then you will just have to say, okay, now I have those two clusters, now I take an example of each of them and I give them a name, class 1 and class 2. But still you can use large amounts of data that have not been annotated. And annotation is costly. So having unannotated data is something you can do. So there is a famous algorithm called k-means to really build clusters of data points. And it's very simple, and I will show it graphically. You have those points, the dots, the small dots. And they are not labeled. They all belong to well, they don't have a class. And you want to build a classifier with 4 classes. You assume that you have 4 classes in your points. Here I have few points, and you see it's just an example. Here I have many more. But obviously they cluster nicely because you were clever enough to choose the features such that they cluster nicely. But you don't know which one is which. Let's take the simple case. I have those points, and I want to find 4 classes. The k-means algorithm is this one. You initialize, pam, pam, very much like your linear classifier. Random. Not totally random here, but somehow. And then you really basically say, now, okay, this classifier, 2 lines, creates a classification. Those 1, 2, 3, 4, 5 points belong to the same class with that classifier. Those 3 belongs to the same class, those 3 and those 3. If they belong to, I was wrong, rewind and replay. Rewind. I initialize by setting 4 centers, 4 isocenters, 4 centers of the distribution, if you wish. This is my initialization. Those 4 points, because they are there, they're supposed to be the prototypes of my 4 classes, the centers. And I will say, okay, in this k-means, I will use a simple rule, which is the Euclidean classification, Euclidean distance. If those 4 points are the centers of my 4 classes, that means that the boundary between the classes are those 2 lines. That was my error, sorry. Right? So those 5 points belong to that class, those 3 points belong to that, 3 and 3. Now, I see 5 points belonging to that class. Then I can update. If they belong to that class, I can update the position of my center to put it really in the center of the 5. If this is the center of those 3 points, I should put the center at the center. I should put it here, and I should move it here. This creates another series of 2 lines. Instead of being there, they moved, so this line is now here, line here, line here, line here. This changes a little bit my classes because suddenly these points move there. So my center will be recentered a bit there, that one will move backward. And iteratively, from an initial position of the centers, iteratively, you build a partition of the space in 4 clusters. And you come up with identifying the centers, in this case 1, 2, 3, 4, 5 centers. And now your classifier is built. You receive a new point, you classify it to the closest center. And you just have to give a name to those classes that now are identified. Is it a good algorithm? Yes. It doesn't mean anything, so I can say. In which case do you think that it is a very good algorithm? If by chance, blah, blah. If by chance your data were drawn from Gaussian distributions with the same covariance, with a covariance which is diagonal and with equal probabilities, because in that case the Euclidean distance applies. But still you can do it if you don't know. This is the most famous unsupervised classification algorithm, K-means. Yes?
You also need the right number of class.
Of class. You have to estimate it. Not from the data. This is something you have to guess or to know from a priori. There are also ways to estimate that from the data by building different number of classes and see how compact they are. But indeed, this is an information you need to have. Okay? Voila, I'm done. That's all I wanted to say. In this course, my goal was to give you the tools to go further, to learn by yourself and to design by yourself more sophisticated things than what I have seen. I have seen the basics of segmentation. I have seen the basics of feature extraction. I have seen the basics of classification. I really trust that with those tools, you can now really understand more sophisticated methods that you might see in other courses or that you might want to implement in your real life. So I don't mean that everything is seen in this course. I mean that you have enough tools to go further and really deeply understand the more sophisticated methods. Many applications, many different methods, but use the same foundations. And that's the end of the course, at least of the lectures. So again, next week another lab, and then we start the robots. And I will, what should I do? Yes, there will be the introductory sessions, 2 of them. The interviews schedule will be set by, surely by Monday, hopefully before. So I look forward to seeing you face to face. That will be simple. It will be 15 minutes talking about the course. What you have to really learn is really, it will be useless to come with the slides and just read them when in front of me. That's useless. So you have to make sure that what I have seen, when you read them back, you understand perfectly. If you understand everything, you will be able to re-explain. You will be allowed to have what you want, the slides with you. But it will be too late to read and say, oh, by the way, I didn't understand that. Can you explain again? No. That doesn't work. But if you're able to re-explain, it's very much like in real life. You will be allowed to go back to my course when you will have to solve a problem, of course. So that's the same rule here. But I really want you to spend a little bit of time trying to see if you understand everything. That's very important. Now you remember the weighting of the different parts, the labs, the project, and the interviews. It was in my first slides. So there will be 3 contributions to the final mark, not only the interview, of course. But I really look forward to meeting you. Okay? Don't forget to fill the evaluations, and I will see you anyway for those interviews. And in the meanwhile, I wish you a very good weekend and a good lab and good robot project. See you soon. Thanks.